Hello and welcome to another Arlington High School Math 4 Honors lesson. I'm Kirk Weiler and today we're going to be doing Unit 11, Lesson Number 2, Absolute Extreme Values, a review. So in this lesson what we're going to be looking at is the absolute maximum and minimum values that a function can attain on a closed interval. This is a review lesson, so we did one earlier in the year on this topic where we developed it more fully. If this is your first look at absolute maxima and minima, this is not the lesson to do it in. All right, because we're going to be throwing all sorts of things in there, including polar functions, so you really don't want to go there. But let's jump right into it. Let's review how to find the absolute max and min values of a function on a closed interval. All right, let's see what we can remember. Exercise 1. Given a function f on a closed interval a to b, the maximum and minimum values of f can occur at only two types of locations. What are they? All right, pause the video for a second and think about this. All right, so hopefully what you remember or what you've seen previously is that they can occur at the endpoints of the interval, the endpoints a comma b, or they can occur at critical values. And for the most part, critical values are locations where f prime of c equals 0. All right, again, let's make sure that we kind of understand this. I'm going to just really quickly draw a couple set of axes, right? Let's say that we have these axes. Let's say we're going from point A to point B. Let's say that we have something that looks like this, right? It's very obvious that we've got our maximum y value, f max, here. It's also pretty obvious that we've got our minimum value here. Right, notice that this is actually the location of a critical value because f prime of, if you will, c is equal to 0 there. This is not a critical value, but it's an endpoint. So this is absolutely critical to understand. When we're looking for the largest and the smallest y values on a function, the largest and smallest outputs to a function for a given input interval, a to b, then really it's very algorithmic. We need to figure out where we have horizontal tangent lines, and then we just need to be able to evaluate the function at the endpoints and at those horizontal tangent lines. All right, so we're going to get right into that. I'm going to clear this out, so copy down anything you need to. All right, it's gone along with our axes. And let's take a look at a problem. It says find the maximum and minimum values of g of x equals 8x minus 2x squared on the interval -3 is less than or equal to x is less than or equal to 1. And again, what I really want you to understand is that the question is very, very easy to interpret. I want the largest and smallest y values. In the last lesson, we reviewed the absolute max-min theorem, which guaranteed that with a continuous function, we would have a largest and smallest y value on a closed interval. Now we just need to find them. Pause the video now and see if you can remember how to do this. Think about exercise number 1. All right, let's go through it. Well, we know that that largest and smallest y value can occur at either -3, at 1, or at a critical value. So first things first, let's find g prime of x. That's going to be 8 minus 4x, right? If we set 8 minus 4x equal to 0, we get -4x is equal to -8. Divide both sides by -4, and we get x is equal to 2. Right, so we have one critical value, x equals 2. We've got two endpoint values, so we're going to evaluate g of -3. It's going to give us -24 minus 18. Is that right? Yep, which is going to be -42. Then we're going to have g of, let's go with 1, so that's going to be 8 minus 2, which is 6. And then we're going to have g of 2, which is going to be 16 minus, let's see, 4 times 2 is 8, which is going to be 8. So it appears that that is our absolute max, and that's our absolute min. It appears to be the case. But this is most certainly not our absolute maximum, right? And it's not our absolute maximum because x equals 2 is never hit, right? We never hit x equals 2. We just don't hit it. So in fact, this is our absolute minimum. That's definitely the smallest y value. But this thing, our 6, well, that's our absolute maximum. I'm sure some of you that were working through this the entire time thought, oh man, he's just making a mistake there. He's not even paying attention to it. So when you find your critical values, it's not a bad idea to immediately check to see if any of them don't fall in the interval, and then you can just cross it out. You don't even need to do this analysis here, right? Because 2 is never hit. I always tell my students it's the equivalent of saying, determine the population of the largest city in the United States, and then saying, well, okay, New York's got a population of, let's say, 8 million, Los Angeles, maybe a population of 12 million, Mexico City, a population of 15 million, so it's Mexico City. Well, it's not Mexico City. Mexico City's not in the United States. We shouldn't even consider it, right? Along with Tokyo and a lot of other places. Anyway, Delhi. Okay, I'm going to erase this, so make sure to write it down, and remember one thing. The interval is as important as the function itself. Never forget the interval. Here we go, clearing it out. It's gone. All right, let's go on to the next page. Exercise 3. An object has a velocity given by that function. What is this object's minimum acceleration on the interval 0 to 4? All right, I think you have every tool you need in your toolbox. Pause the video for, I don't know, let's say 5 minutes and try to answer the question. All right, let's go through it. This is actually kind of a tricky question. I modeled it after an AP multiple choice question because a lot of students will just say, all right, no problem. I'll take the derivative of the function they gave me. That's very, very easy. By the power law, it's t squared minus 6t minus 16. I'll set this equal to 0 and I'll go. The problem is, no, that is the acceleration function, right? The acceleration is the derivative of velocity. So in fact, this is the thing that I want to minimize. I need to minimize this. Oh, too many dots. I need to minimize this function. In other words, the first derivative, just finding the derivative the first time, that was all about just finding the function that I want to find the minimum of. Right now, I need to find its derivative, a prime of t, known in physics and engineering as the jerk, but nothing that you have to know here. All right, so 2t minus 6 is the acceleration. Take 2t minus 6, set it equal to 0. Easy enough to solve. T equals 3. Take a look at my interval, or at least try to look at my interval without the arrow there. T equals 3 definitely falls in it. So now let's figure out a of 0. That's negative 16. Let's figure out a of 3. It's going to be 9 minus 18 minus 16, which is negative 25. And let's figure out a of 4, which I will save you the arithmetic as negative 24. There's our winner. This is amen. Amen is negative 25. All right, very tricky. It was multiple choice on the AP, and that was especially tough because, of course, they definitely gave the analysis where they did the single derivative. They got the a of t, set that equal to 0. Oh, not good, not good. All right, anyway, kind of a neat problem. And again, not hard, but you have to keep your eye on the ball. Make sure that you know the math, not just the algorithm. So I'm going to clear this out. Okay, here it goes. Let's go on to the next problem. All right, exercise 4. This is going to get a little more ugly. Find the maximum and minimum values of y equals ln of x plus 6 plus 1 over x on the interval 2 to 10. Okay, obviously this is going to be kind of a mishmash between calculator and non-calculator. I'd like you to try to do as much of it as you can without your calculator. But again, you have every tool you need at this point. So pause the video, take up to maybe 10 minutes to do this problem, and then play the video again when you're ready to see the solution. All right, let's go through it. So, got to find the maximum and the minimum values here. Nothing particularly tricky. I'm going to find dy dx, and I'm going to do it in red. All right, so to find the derivative of ln of x plus 6, we're going to use the chain rule. That will be 1 divided by x plus 6. I would then have to multiply it by the derivative of the inner function due to the chain rule, but that's 1. All right, here, if I take the derivative of x to the minus 1 using the power law, that will be negative 1 times x to the minus 2. I'm going to just clean this up a bit because I don't need it to look this bad. 1 over x plus 6, 1 minus x squared. Oh, look at that. That just looks horrible. But whatever, right? We're pre-calc students who are doing calculus right now. So I'm going to separate those. I'm going to cross multiply. I'm going to get everything to one side. I'm going to factor because I'm biased towards factoring. Ooh. Apparently I'm biased towards making mistakes too. See, that's right. X equals 3, x equals negative 2. All right, go back, look at the interval. We can definitely cross this thing out, and here's our one critical value. Wonderful. All right, for whatever reason, we're going to go back to blue. Now here's where the calculator comes in. There's really no way to evaluate these on sort of their own merits, but I'll get ln of 8 plus 1/2, which is 2.579, accurate to 3 decimal places. Y of 3 will obviously be ln of 9 plus 1/3, which is 2.531. And y of 10 is ln of 16 plus 1/10, which is 2.873. Let's go back to red. Here is my absolute min, and here is my absolute max. You know, there aren't a lot of things in calculus that are algorithmic, meaning that you just do step 1, step 2, step 3. But absolute max min problems, they are. Notice, by the way, in this problem that they never use the term absolute, because they really don't need to. If I tell you to find the maximum temperature during the summer, I don't need to tell you that it's the absolute maximum temperature. I mean find the largest temperature of the summer, right? It's only when we're talking about relative maxes and mins, right? These sort of like temporary turning points, things like these guys. It's only these things that I really have to specify in terms of relative, okay? So just make sure you make a note of that. I'm going to clear this out, and then we're going to go on to the next exercise. We're speeding through this lesson because it's review. Okay, here we go. Gone. Let's do the next problem. All right, exercise 5. Find the largest and smallest values of r for r equals theta plus cos 2 theta on the interval theta greater than or equal to 0, less than or equal to pi. Do as much of this problem as possible without your calculator. You will need it to ultimately decide on the values. I can't apparently read my own problem. Anyway, so look, this is really no different than if I had y and x. It really isn't, because at the end of the day, I could still graph r versus theta, and I could still have a largest r and a smallest r. So do the same thing. Don't graph r versus theta, but you know, do the same kind of procedure as you did before. Pause the video now. I'm going to erase this. All right, let's go through it. It really is the same procedure. There's nothing different. Right, dr d theta, that's going to be 1 minus 2 times the sine of 2 theta. Think about that for a minute if you need to. Right? It's a little chain rule, but it should be pretty easy. I'm going to set this equal to 0. This is a trig equation, so that takes a little finesse to solve. We're going to have sine 2 theta is a positive 1/2, right? Now sine, that's positive in 1 and 2. Remember, my angle is 2 theta, so 2 theta will go between 2 pi and 0. All right, so 2 theta will either be pi over 6 or 5 pi over 6, which means theta is going to be pi over 12 and 5 pi over 12. All right, that's it. Just making sure, you bet, those are my critical values. Now I just have to figure out r of 0, which will be 0 plus the cosine of 2 times 0, which will be 1. I I need to figure out r of pi over 12, which is going to be pi over 12 plus cosine of pi over 6. How much of this we end up doing without our calculator and how much we end up doing it with our calculator kind of boils down to when we feel comfortable. We'll come up with a decimal eventually. R of 5 pi over 12 will be, obviously, 5 pi over 12 plus the cosine of 5 pi over 6, which is going to be 5 pi over 12 minus root 3 over 2. And then finally, r of pi will be pi plus cosine of 2 pi, which is pi plus 1. Now, it's a little bit tricky, and we could talk a lot about number sense. I mean, I'm fairly certain that r of pi is bigger than r of 0. There's no question about that. So these two aren't too bad. But if we evaluated this, it'd be 1.128. This would be 0.443. This one would be 4.142. One thing that's interesting is that we don't have any negatives here, which is fascinating. It means that the radius never goes negative. So it's pretty easy. Let's go back to blue to highlight what we have. This is actually going to be my minimum and obviously my maximum. So use your calculator right now. We just came out of a unit on polar, at least in Math 4 Honors. So use your calculator to sketch the curve. Put in a theta min of 0, a theta max of pi. You might want to use your answers to help you set the x and the y window. And see what the graph looks like. All right, let's go through it. I'm going to use my handy-dandy program to create a few axes here. All right, and essentially what it looks like is a sort of a weird curve. That's something like this. And it's interesting because this angle right here, something like this, right? This is my 5 pi over 12. It's a little bit hard to get a sense for that angle. It's obviously less than pi over 2. Maybe I didn't draw it quite beautifully, but that is definitely my minimum radius. My radius starts off at 1, grows to be large, not huge, but 1.128, something maybe like out here. Maybe this is my pi over 12. Then the radius starts to decrease until it hits the 0.443, and then it increases again until it gets as large as it's ever going to be, which is 4.142. Excuse me. Whew. Boy, that was fun. Anyway, so a little combination of polar and absolute max min. Certainly didn't see that back in November or December when we were doing this the first time. So we're going to clear this out and finish up the lesson. Here it goes. Okay, so that was a pretty quick review of how to find absolute maximums and minimums of functions on a closed interval. The reason that we threw this lesson in, as opposed to, let's say, throwing in a lesson to review how to find inflection points, is that in the next few lessons, what we're going to be doing is optimization, which I think is one of the most fun things that you do in all of calculus. But really what optimization is it's applied max-min problems, absolute max-min problems. So if you don't remember how to find absolute maximums and minimums, it makes it pretty hard to do it in sort of an applied sense. Anyway, we'll pick that up in the next lesson. For now, let me remind you that this has been an Arlington High School Math 4 Honors lesson. I'm Kirk Weiler, and until next time, keep thinking and keep solving problems.